The next speaker is Marco Mazzucchelli from Lyon, and he will talk about periodic orbits of magnetic flows on S2.
Thank you very much for the invitation. This is my 5th participation to this conference, and I'm planning to come again in the future, just in case. No matter how my talk will be. So it's going to be a talk about periodic orbits of Hamiltonian systems, of a special kind of Hamiltonian systems, which are called magnetic flows. Many people in the audience are actually experts on this topic, but let me remind the setting for everyone. So talk for a while about magnetic flows. So magnetic flows are Hamiltonian systems on, what's going on? No. Are Hamiltonian systems on cotangent bundles. So consider a cotangent bundle. Let's say at this point of the talk, M is just a closed manifold. Later on, it will be a surface and then a sphere. So we all know in this room that cotangent bundles are symplectic manifolds. If you denote the coordinates, local coordinates of a cotangent bundle with Q and P as usual. So Q is a point in M, and P is a point in the fiber of M. You can write down the canonical symplectic form of the cotangent bundle as dq wedge dp. And the magnetic flows, we consider this symplectic form perturbed, or deformed rather, by a term which is a magnetic term. So it's deformed by a closed-to form, sigma. So sigma is a closed-to form on the base M. So if we want to be precise, since we're working on T star M, you have to consider the base projection of T star M. Let's call it pi as usual. And here one would rather take the pullback by the projection. So a little bit of linear algebra tells you that for any closed-to form, this sum is non-degenerate and it's closed. Not exact anymore, though. Okay, so this is the symplectic manifold that I'm going to consider, the class of symplectic manifolds that I'm going to consider. And magnetic flows are Hamiltonian flows on this, which I denote by phi h t. So this is the flow of a Hamiltonian H. And throughout the talk, the Hamiltonian will be a Tonelli Hamiltonian, meaning that it's a classical type Hamiltonian. Sometimes they're called optical Hamiltonians. Tonelli means that the restriction of H to any fiber of the cotangent bundle is a convex and superlinear function. For instance, polynomial of degree 2, positive definite polynomial of degree 2. So convex and superlinear. So this terminology is due to John Mather, I believe. Actually, so the result that I'm going to present is valid for this class of Hamiltonians, but it's interesting enough to consider a subclass of Tonelli Hamiltonians. It's actually interesting enough to consider the metric Hamiltonians. So let's say interesting enough to consider Hamiltonians of the form HQP equal to 1/2 squared norm of P where the squared norm is taken with respect to any Riemannian metric. So with this choice of the Hamiltonian, so let's say for now on, the Hamiltonian will be of this form, knowing that I can generalize whatever I say to general Tonelli Hamiltonians. With a Hamiltonian of this form, this flow is a magnetic geodesic flow, it's called. Basically, this flow models the motion of the particles immersed in the magnetic field given by the form sigma. So the goal of the talk, so we all know that on a Hamiltonian system, on an autonomous Hamiltonian system like this, the level sets of the Hamiltonian are preserved. So my goal will be to study, it's a general problem, to study the periodic orbits of this flow on a given energy hypersurface. So let me just write it as in this way. So I want to study the periodic orbits of this flow on this energy hypersurface, where E is a given energy level. And so for now on, so there's a lot of literature on this problem. Maybe I can just mention, if there's no sigma, this is the usual Riemannian geodesic flow. So the problem of studying periodic orbits is the classical problem of finding closed geodesics on Riemannian manifolds. There's a lot of literature on that problem. So this is, if you want, in a sense, it's a generalization of that. So for now on, let me focus on the case where M is a surface. And I have no time to give all the known results. But let me just mention those which are more closely related to my talk. So let's say some results. So in case, so M is a surface, so it's itself a closed surface, of course. So M is itself a symplectic manifold. So if we assume that the closed to form sigma is non-degenerate, so it's symplectic. So if sigma is symplectic, on the surface, so this is assumption 1 and this is maybe assumption 2. Then if M is, say, not the sphere, there's a recent result due to, it's a combination of a result of Franks and Handel, together with work with a result of Ginsburg, Gurel, and Leonardo. It shows that there are infinitely many periodic orbits. So for now on, let me just write PO. PO is periodic orbits. There are infinitely many periodic orbits on every say energy level with E small enough. And this doesn't work on S2. There's a result of one of my co-authors, Gabriele, that says that there exist either 2 or infinitely many periodic orbits. Again, on small energy levels. So this is the symplectic case, and I'm actually going to focus on a complementary case, so the case in which sigma is degenerate somewhere. a particular, say a classical situation is the exact case. So if sigma is exact, so it's not symplectic in particular. Now what can we say? So there are two subcases. So if we consider an energy level E, which is large, we can also quantify this, how large it should be. So if E is large, then this flow is Finsler. This flow is Finsler. So, so looking for periodic orbits of that flow amounts to looking for closed geodesics of a Finsler metric. And many things are known, in particular on surfaces. Well, on surfaces other than the sphere, there are infinitely many closed geodesics. Yes? Is for small energies. For all small energy. And same in the other results. So coming back to Finsler. So on surfaces of positive genus, there are infinitely many closed geodesics. That's quite elementary. On the sphere S2, it's known that there are always two closed geodesics, and that's optimal. There are examples due to Katok that show that if M is equal to S2, there may be only two. Periodic orbits. And if E is small, I have no space, I'll continue there. If E is small, there's a result I talked about actually in the last instance of this conference. It's a result due to Abbondandolo, Leonardo, myself, and Paternine, Gabriel Paternine. Where we proved that for almost all energy levels E that are low enough, there are infinitely many periodic orbits. So this works for, again, for an exact magnetic form. And this has been generalized to the case where sigma is not necessarily exact, but oscillating. Oscillating means that it's not a non-negative multiple of an area form. So if you want, there's a sign for two forms on surfaces. On some point it's positive, and on some other point the form is negative. It's the oscillation. So this result has been generalized to oscillating forms for M different from the sphere by my co-authors, Lucaselle and Gabriele Benedetti. And what I'm going to talk about today is the remaining case, which is the sphere case, which required a big joint venture. So this is a result of Abbondandolo, Asselle, Benedetti, myself, and Iskander Taymanov. So we need a lot of co-authors. This is somehow the most complicated case due to the fact that the sphere is simply connected and it's spherical. So I'm gonna come back to that in a moment. So in my talk, I want to discuss this result. So first of all, how do we look for periodic orbits of magnetic flows? Where, as usual, with variational methods. Let me talk about variational methods. And from now on, M would be S2. So M will be S2, and sigma will be just a closed to form. So we consider the magnetic flow given by sigma and by some Riemannian metric on a sphere. So it's known that the periodic orbits of our magnetic flow on the energy hypersurface h minus 1 of E are precisely characterized or are given, say, during one-to-one correspondence with the zeros of an action 1 form. If this one form were exact, as it is the case when sigma itself is exact, we have the classical least action principle. But unfortunately, this action 1 form is not exact in this general situation. Or not necessarily exact, maybe. Okay, so this, so we're forced to work with 1 forms instead of with action functionals. Working with 1 forms is not particularly nice, so let's force ourselves to work with action functionals by passing to the universal cover of a loop space. So let me explain all this in detail. I denote by calligraphic L. It's the loop space, but let's be a bit more precise. This is the space of periodic curves on S2 with any possible period. With any possible period. So just a technical detail, maybe for those who are familiar with this kind of problems. This is an infinite dimensional manifold, and a way you can see it is by remarking that this, you can represent it as the space of 1 periodic curves on the sphere S2, which is usually denoted by lambda S2, times 0 infinity, which encodes the period of the curve. But this is just a technicality. I'm not going to enter into this in a talk. All right, so on this space of loops, we can consider the usual Lagrangian action functional. I denote it by SE. So I keep track of E because it's the functional that gives that is related to the periodic orbits problem on this energy level, h minus 1 of E. So this is simply SE. So SE of a periodic curve gamma, where gamma, say, is period, for instance, tau. Is simply the integral from 0 to tau of the squared norm of gamma, maybe 1/2, plus the period, tau, that multiplies the energy that we fixed, E. So this is not a constant because the period varies in the domain of our function. So it's part of the data. It's part of the domain. All right, so this functional doesn't provide the variational principle that we need for our periodic orbits problem. If you look for critical points of this action function, what you find are closed geodesics, classical closed geodesics on the sphere, parametrized so that they have energy E. So it's not what we're looking for. And it's not what we're looking for because, as we said, there's no action functional for our problem. So let's now pass to the universal cover of the space of loops with any period. So I denote it by L tilde. So this is the universal cover of the free loop space L. And as usual, the universal cover can be realized as homotopy classes, the set of the family of homotopy classes of paths. Let's say a path I denoted by U. So it's a path, so a map from 0, 1 to L, such that the path starts, say U of 0 starts at, let's say, for instance, the constant loop of period 1 at an arbitrary point of S2 that we fixed once for all, let's say the North Pole, or the South Pole, since we're in Brazil, the South Pole. Okay, so this is the universal cover. I didn't define the action 1 form, but this action 1 form can be lifted, of course, to L tilde. It becomes exact, and I give you directly the primitive of the lift. I denote it by SE tilde. So SE tilde is not just a lift of SE, it's something more. So SE tilde of, let's say, an element U. From now on, I'll forget to put the brackets, but let's just keep in mind that we need the homotopy classes, not the actual path. So SE of a path U is simply the action of U of 1. So once again, U, you should visualize it as a path. So it's, if you want, it's a periodic curve. It's a family of periodic curve that go to a constant loop at the North Pole, at the South Pole. So, well, this is how you visualize your U. So U of 1 is the final periodic curve. You take its action plus the integral over U seen as a submanifold, or actually, it's not necessarily submanifold, but by transversality you can deform it to be a submanifold of the non-exact magnetic form sigma. Okay, now with this function, it turns out that U is a critical point of S tilde E, if and only if U of 1 is a periodic orbit of our magnetic flow on the energy level of value E. So I'm being a little bit imprecise here. I should say is the projection of meaning that this is a submanifold of the cotangent bundle of the sphere, but this function works on curves on the sphere itself. But on a classical system like this, given a an orbit of this flow is completely determined by its projection on the sphere. Okay, if you want its lift, it's just the velocity vector or the velocity covector.
Sigma is supposed to be exact.
No, sigma is not exact. Close to form. I'm talking about degeneralization. So the exact case was maybe let's say this was a statement about exact, and then this statement has been generalized to the case of sigma oscillating. But for now, I'm not even assuming that sigma is oscillating. If sigma is exact, you see that this functional becomes invariant under the deck transformation. So you have a function downstairs, but not in this case. Actually, let me explain that because I need it. So a little bit of elementary topology. So the universal cover, on the universal cover of our loop space, we have the action of the deck transformation group, which for the universal cover is simply the pi1 of L. So here we have an action of pi1 of L. And pi1 of, so L is just the loop space of the sphere. So it's well known that pi1 of the loop space of the sphere S2 is just Z. And you can write down explicitly a generator. Let's call it little z. So let's give a name to the south pole. I call it S. Say. So what is little z? Little z is a loop of loops that you can draw. It's this. So here's your sphere. This is the south pole S. So Z is, if you want, is a map from 0, 1 to L. So Z of t is a loop itself. And so Z of 0 is the constant loop there. And as t varies from 0 to 1, you get loops that wrap around the sphere. So this gives you an element of pi1 of L, and it turns out it generates pi1 of L. This is very elementary. Okay, so and now these acts. So these acts on L tilde just by concatenation of loops. So if you take now Z, if you take U, which is an element of L tilde, and you act on it by Z, the action is just the concatenation action. So these are two paths in the loop space. You concatenate them. Okay. So let's see how the action functional SE tilde behaves under this action. So you see this part here is not affected by the action of pi1 of L, but this part is. And so we see right away that SE tilde of Z star U is precisely SE tilde of U plus a constant, which is simply, well, it should be the integral of sigma over Z, but Z wraps around the sphere, so it's just the integral of sigma over S2. Okay, so this is the variational setting. Now, so I mentioned that this result, the result that I'm going to present, I haven't written it down properly yet, but it's a result about periodic orbits for almost all low energy levels. So let me talk about relevant energy levels now. So what are the relevant energy levels? The first relevant energy level is the minimal energy. So for our Hamiltonian is 0. So remember the Hamiltonian, I raised it, but it's simply the squared Riemannian norm. And the second relevant energy level, in the exact case, it would be a Magnier critical value. You can call it like that in this setting too, but it's a bit, the definition is a bit different. So I call C the supremum over all the energies E larger than or equal to the minimal one, such that there exists an open subset of S2 with smooth boundary. Smooth boundary, say, so the boundary is smooth, and therefore it's a union of finitely many, well, it's smooth and it's a union of finitely many periodic curves, say gamma 1, gamma k, for instance. And such that, so if you sum the action of these curves, plus the integral over sigma of little sigma, this is negative. So this is a bit of an unusual definition. It deserves a bit more comments, but luckily Mazzucchelli is going to talk a lot about this in his talk, I guess. So I won't say much for my talk, but let me just comment a couple of things. So first of all, so low energy level will mean energy levels between 0 and C. So we have to make sure that these two values are not equal, and sometimes they are. So let me maybe just mention that if sigma is exact but not identically 0, then C is positive. These two values are different. And more generally, this is also true if sigma is oscillating. It's been shown, well, this was implicit in Taimanov's paper, but it's been showed by Mazzucchelli and Gabriele Benedetti. And so here's the first theorem that I'm going to use. So theorem. This is due to Taimanov and independently to Contreras, Macarini, Leonardo, and Paternine. It says that any energy value between 0 and C possesses a periodic orbit, let's say gamma, so with energy E. It's a periodic orbit of the flow on H minus 1 of E. And we can say a little bit more, and I will need that more. And actually, if you take any U in the universal cover of the loop space, such that U is a lift of gamma, meaning that U of, so with U of 1 equal to gamma, then U is a local minimum of S tilde E. So once again, Mazzucchelli in his talk is going to go back to this theorem. So I'll just leave it like that, and I'm going to use it for my main result, which is, let me write it this time precisely. So it says that, so this is a result of all my co-authors. says that for almost every energy levels E between 0 and C, there exist infinitely many periodic orbits. Can you read the result? For almost all energies E in this range, there are infinitely many periodic orbits. Questions? No. So I have 20 minutes left. I want to give a sketch of the proof. Sorry, 25? Ah, great. Great. Slightly less sketchy sketch of the proof then. The proof is a bit involved, so I won't be able to give you all the details, but at least I'll be able to show you the difficulties and what are the ideas to go around them. So the starting point is this theorem here. So let's first fix an energy level E in our range. And let's consider this periodic orbit found in the previous theorem and the associated local minimum of the action. So fix E and fix U, which is the local minimum of the action as C tilde. So first thing which is not entirely obvious is that a local minimum gives us a z squared worth of local minima. So let me explain that. If you now take, say, an integer m, larger than or equal to 1, you can consider what I denote by, so this is a local minimum, so it's a point in the universal cover of the loop space. So I can consider its nth iteration, so to say. I denote it by um. So um is again an element of the universal cover, and it's defined like this. I draw it. So if u was our path of loops, u to the m is going to be, so consider this as a pinched cylinder. U of m will be the m-fold cover of that cylinder that it's going to get pinched. So it's a path of loops, and at every instance you have the m-fold cover of the original loop here. So in particular, u of 1 is the periodic orbit found by the theorem, and um of 1, it's its m-fold iterate. Okay? So, so one statement that is not obvious, it's for geodesic flow, it was remarked by Edland. But in this setting, it's due to Abbondandolo, Macarini, and Paternai. So this statement says that since we are on an orientable surface, the sphere, and since we have a local minimum, when we iterate it, we still get local minima of the energy. That's something that doesn't work on higher dimensional manifold, even for geodesics. When you iterate a closed geodesic that is a global minimum, its iterate may not be a global minimum. For instance, its Maslov index could grow, even though the original Maslov index was 0. So let's say u to the m is still a local minimum. Well, and then if we act on u with pi 1 of L, so we consider z star u to the m, well, the action functional is equivariant under the action of pi 1, so it varies by a constant. So this will still be a local minimum. Local minimum of our action function as C tilde. So therefore, we have a family of local minima parameterized by two integers, a positive one and another integer. So let me call maybe, let's see, let me call u n comma m. this is u iterated m times, and you apply to it z n times. Okay, so we have a family parameterized by n in z and m in n, and these are all local minima. So when you have a function that has many, many local minima, you can try to join them with path and do min-max to detect other kind of critical points. So let's do some min-max. So I consider a min-max value which is parameterized by 4 integers, n0, m0, and n1, m1. And this is just the infimum over some path p of the maximum of SC tilde restricted to p. So what is p? P is a path on L tilde. So this infimum ranges over paths on L tilde, joining u n0, m0 with u n1, m1. So p is, this is p. All right. Yes. So it's known that for this kind of problems with low energy, there may be lack of compactness. So when you do min maxes, you may end up finding values that are not critical values of your function. So you may not find other periodic orbits. Nowadays we know how to circumvent, to some extent, these issues, thanks to a trick due to Struve, but imported in this old business by Gonzalo Contreras. And let me be a bit imprecise here, but I think it's enough for this presentation. I can just say that this value here, C, is a critical value of SC tilde for almost all energy levels E in 0C. So this is not a very precise statement, but the entire truth is that there's a way to modify this recipe so that min-maxes provide critical values in this setting. So this, if you want, is a difficulty in the proof. Let's assume, let's go around this. It was a difficulty already in the exact case and in the other statement, so the experts know how to deal with this. So let's say that for now on, for all choices of these integers, C is a critical value of SE. And that's where the almost all energy in the statement comes in. So I continue here. Now, so now, so four indices are too many to keep track of. Let's get rid of 2. So let's consider C and 0, M0, which I define as the infimum, or N1 in Z and M1 in N of C and 0, M0, N1, M1. So I'm taking the infimum over many min-max values. And this is, a priori, this may not be a critical value. Taking infimum of critical values, well, the set of critical values in a function that doesn't satisfy Paddy-Smith is not closed. But it's a real number. Because it's, well. And one can easily see from the very definition of this value that if you take N0 and you add an integer to it, so k is an integer, this sort of min-max value gets shifted by k times the integral of sigma. So plus k integral over S2 of sigma. Okay, so then you see I'm working with the universal cover because on the loop space I have no action functional. But these properties of the min-max value allow me to somehow recover the action in a certain window. And say I can choose, this allows me to define, so sorry, this is M0. This allows me to define C of M0 as C of N0 M0, where N0 is the unique integer such that this value here belongs to the interval 0, integral of sigma. Okay? And now I claim that I claim that these values, well, I would like to say these values provide the action values of infinitely many periodic orbits, but it's not quite true. The argument is a bit more involved. So here's how it goes. So we have this min-max scheme. Once again, I have this min-max parameterized by these 4 values, and then I get rid first of the last 2 values, and then of the second value as well. So given a min-max like this, let's simplify things. Let's assume I can find an optimal path, the path that reaches, that realizes, that achieves the min-max. So it goes like this, more or less. So let me draw the action as the height function in the blackboard. And so I'm doing min-max from paths from u n0 m0 to u n1 m1. So u n0 m0 is some point here. And u n1 m1 is some point in L tilde. So the blackboard is N tilde, L tilde. And let's assume I can find an optimal path P for this min-max. That means it's a path that joins these two points in L tilde, and it stays below the min-max value C. Except at some points which are mountain passes. This is an optimal path that realizes the min-max. Okay? So since C is a critical value, we can find an optimal path like this. So this is P. P is an optimal path. That stays below the critical value and goes through mountain pass critical points at the critical value level. So V is a mountain pass critical point, so it gives a periodic orbit. And here I'm going to use a big black box, which was contained in my paper with Abbondandolo, Leonardo, and Paternine. And this says that if you take an optimal path and the optimal path goes through a mountain pass at the critical value, this V here, so this is V is an element of L tilde. So V of 1 is a periodic orbit, but V of 1 cannot be too much iterated. The reason being, so you should imagine that the domain, your domain has some topology. So here you have some mountains, and here you're crossing a mountain pass. But if a curve is too much iterated, if V is too much iterated, the geometry looks more like this. Like this is V, and the geometry looks more like this. So when you have a path that goes through through here, you can slide it sideways and find another path that stay below the min-max level. And that contradicts the definition of the min-max. So this is not a proof. This is what happens, but one has to prove it. Okay, so let's see if I have 10 minutes left, right? Okay, good. So I should be able to get to a conclusion. So, all right, so now what do we do with these min-maxes that we found? So I want to find infinitely many periodic orbits, so let's assume we don't have that. And since we only have 10 minutes left, let's assume that we only have one periodic orbit. I show you that it's not possible. And then it's the same argument will tell you it's not possible to have only finitely many. So assume there exists only, well, not only one periodic orbit, but only one mountain pass periodic orbit. Only one mountain pass periodic orbit and all its iterates, of course. And I show you that this is not possible. Actually, there must be infinitely many mountain pass periodic orbits. So I just said that if you take high iterates of this mountain pass, you don't get a mountain pass anymore. So let's simplify again everything. Let's say that if you take V and you iterate it, remember I put an M here for iteration. So when I iterate it M times, it turns out this is not, let's assume that this is not a mountain pass. For every M strictly larger than 1. So once again, if you have a mountain pass and you iterate it enough, it's not of mountain pass type anymore. It's something else. So let's simplify things. Let's say that once you iterate it twice, that's enough to destroy the mountain pass property. Again, this is just a cosmetic advantage for the rest of my proof. In general, this is true for some M larger than a constant. Okay, so these two properties imply that our function, our value C of M0 is a critical value. Do you see this? Maybe not. So let's see, we know that this is the infimum of several min-maxes. So this is larger than or equal to, for instance, SC tilde of U N0 M0. Remember, CM0 is the infimum of C N0 M0. CN0 M0 is the infimum, is the min-max of paths going from U N0 M0 to something else. Therefore, the min-max is higher than that, has higher action than U M0 N0. And so this is finite, and then this is also less than or equal to, by the very definition of CM0, C of M0 N0 and sum N1 N1 for any choice of M1 N1. So this is a real number, and this is a real number. So now C of M0 is contained in a compact interval, and it's obtained as the infimum of critical values in a compact interval, but you only have one mountain pass and all its iterates. So you only have one mountain pass V and all its shifts by Z. Therefore, you only have finitely many mountain pass critical values in a compact interval. Therefore, you're taking the infimum over a finite set, so it's a minimum. So this CM0 is actually a critical value. It's a bit complicated, but not, it's more complicated to spell than to understand, actually. So this is a critical value of SC tilde. And now we're almost done. I claim that this produces with one last ingredient, a contradiction to the fact that there are only finitely many periodic orbits. And I need one more ingredient for that. So the one more ingredient is the following. It sometimes surprises people from outside the field. If I give you a smooth function on a manifold, a finite or infinite dimensional manifold, and this smooth function has finite Morse index, and let's say finite nullity at the critical point, then this critical point has a finitely generated local homology. So maybe spelled like that, it's a bit fancy, but let's see what it means for a mountain pass. For a mountain pass, it means that, let's say that this is your mountain pass V. And let's say that V has a critical value C. So this is at level C. So nearby, let's keep track of the regions of the region where SE is less than C. So the sublevel sets near this, and it will be a union of several regions. So these dashed regions are the regions where the function SE is less than C, the sublevel sets of our function. Well, it turns out that there are only finitely many such components of the sublevel set. So it's only finitely many. All right, but then the picture is a bit messy, so let me maybe erase what I just wrote so that I keep the picture simple. So once again, a mountain pass periodic orbit, if you look at it as a point in the domain of the action functional, and you take the regions where the action functional has value less than the critical value, well, these regions are this region is made of finitely many connected components near the critical point. It's a down-to-earth way of saying that the local homology of a mountain pass is finitely generated. And it's a general nonlinear analysis property of critical points of good functions. Okay, but then I claim that this finishes the proof. Why? Because consider now our values C of m that I defined over there. And C of m are critical values as for every m in n. And now, as you vary m, so C of m will be equal to C of m n of m for some value of n. And as you vary m, remember, this was a min-max on paths starting from the point u of m n of m. And now you have infinitely many minima and only finitely many components. So it turns out that for at least two values of m, you must have the corresponding minimum that belongs to the same connected component of the sublevel set. I'm going a little fast, so let me take 30 more seconds and repeat this, maybe. So I said, nearby the mountain pass, there are only finitely many connected components of the sublevel sets, of the sublevel set corresponding to the point. Now take our sequence of min-max values parameterized by the integer m. And we know that this is obtained as some min-max on paths leading from a minimum u of mn. Now vary m. So this u of mn is contained in a sublevel set, so it will be containing one of these connected components, but there are only finitely many of them. So eventually, by the pigeonhole principle, if you want, eventually you will have two values, m1 and m2, that are different, so that the corresponding minima will belong to the same connected component of the sublevel set. But then you can join them with a path the state in the sublevel set, but this path is one of the paths in the min-max family, and therefore the corresponding min-max value that you obtain would need to be less than C of M, which is the value of V. So this last part was a bit complicated, but it's, this is the proof. And I stop here.